My name is Dongjie. I'm a data scientist in CARTO. It's a great honor to be here. And today I'm going to talk about cooking with spatial data science because I've watched too many episodes of Anthony Bourdain's Parsano and too many scenes. So yeah. So when I think about what should I do in this presentation, what the title of this presentation is, everything in my mind is about food. Still food. Yeah. So, well, I know this presentation is, it's definitely not about food. But as a foodie, I think there's something in common between food, cooking, and doing some fun stuff, interesting projects in data science. So, still food, sorry. So today I'm going to talk about what we have been working on in CARTOS as a data science, the member of the data science team. And basically I will focus on the third part, the data, spatial analysis, methods, algorithms, and then the use cases and solutions. So I will show them one by one and talk about how those three components work together in CARTO. Well, so let's talk about data. So as a foodie, I think data is just like the raw ingredients. And the comprehensiveness and specialty of the raw ingredients, I think are always the essential part for example, for a chef to run a high-rating restaurant. So the first data stream I wanted to highlight is the food traffic data that we apply to several projects in CARTO. So the food traffic data, also we call cell phone mobility data. There are many different types of this cell phone mobility data. So earlier, more the academic research tended to use what we call detailed record, the CDR data, and they are usually from the telecom companies themselves. And so as we know now, it's the age of application and smartphones, smart devices. So a lot more of the data that we are looking at today, application GPS data, which collected by your application, your phone, your smartwatch or something. And so those data turn to have a higher frequency of pins than the CDR data, but at the same time, they are varied in terms of the quality. So this map shows that what the raw GPS data look like. If you zoom in this map, so that each point represents a GPS pin collected by your app, and always so for each pins we always have some attribute attached with them. For example, the anonymous user ID, timestamps, latitude, longitude, application ID, and also the accuracy. So. So as we know, it's not easy to get insight directly from the raw data. So CARTO has been trying to create different types of the derivative data sets from the raw data, and then we can use those derivative data sets for potential use cases like site selection, traffic management, and so on. So a big question here is so the data. So a lot of people will say, "Oh, so your data are representative for the whole the data around the world." So actually, before we use those data to do the analysis, we did a lot of evaluations to prove that the representativeness of those data. For example, we compared the census populations and the aggregated mobility data from those two maps. So the patterns kind of similar, and also we wanted to find out the correlations between the population and the numbers of the home locations we detected from the GPS data, and we did, like, for example, the Spearman correlation, the Pearson correlations, and it turns out the data we are using actually is good enough in terms of the quality. And that's a evaluation also for avoiding the bias of the data. Okay, so I want to show some some examples that we did using those foot traffic data. So in this case, my teammates once they used the GPS data to do some traffic impact study on the Mass Avenue in Boston. So this map shows the type of the derivative data I mentioned. You could say those GPS pins colored by the travel mode, and the green pins detected as a car mode. So you could say most of them along the road network, and the pink and yellow pins, which represents the pedestrian and stay mode, they are more likely to appear in the urban area. So which makes sense. And if we zoom into the Mass Avenue, our target area, these two animations shows the comparison between the car mode and the pedestrian mode. The white of the road represents the counts at different hour of day. Actually, behind these two animations, we did a lot of heavy work. For example, we have to do a lot of cleaning and to filtering out the outliers, and also we need to split the pins into trips, detect the travel modes, and also do the aggregations by each road segmentation. So another type of derivative data we commonly use is the origin-destination matrices, also generated from the raw GPS data. In these two maps, the right point actually is here, is the location of our CARTO office. So here I wanted to know, so here I just take that gray cell, this neighborhood as a destination and the origin respectively, and we wanted to know where people come from and go during a specific time period. For example, here is 8:30 to 9 a.m. And with these OD matrices, actually we could do more. One example is to plot the mobility catchment area. So a catchment area is a geographic area for which a facility attracts its customers. It's defined by the targeted locations and also the distance in seconds, which can be reached from your target. So normally we use these isochrone buffers, for example, the 30 minutes drive isochrone, the 30 minutes work isochrone to represent the catchment area for a specific merchant. But since we have got the OD matrices, we have the new data streams, then we can use the GPS data to plot the mobility catchment areas. If in this case, if we pick one restaurant in Los Angeles as our target, means as the destinations, then we could show the OD counts during 8:30 to 9 for that gray cell. So here we can see the shape of the mobility catchment area is kind of more irregular, and compared with the orange 30 minutes drive isochrone, so the mobility catchment area is more kind of compact. So kind of to some extent, you could say this mobility catchment area is more realistic to reflect on the where people really come from, yeah. And another so this is like the full traffic data. Another valuable data stream we are using to do spatial analysis is the traffic data, including the traffic volume data and traffic jam data. So my teammate Michelle combined these two data streams as well as the New York City open data to do some crash predictions in New York City. And I think this type of data will be much helpful for the transportation planning agency or other departments to make decisions in transportation planning and to do some analysis on the traffic flow. Well, a third data stream that I wanted to introduce here is the MasterCard retail location index data. We call MRLI data. So MRLI data provides the insights on the sales-based performance of the retail locations. They are anonymous and aggregated data, and they converted it into 5 component scores. So, for example, the sales is the ranking of the total monthly sales by each location. And this data frame will be useful for the use cases such as the site planning, property valuation, or marketing, and so on. So Yeah, so that's the first part, the data. And yeah, if we say the data is the raw ingredients, then the method, the algorithm is about how to cook. So in CARTO, our data science team, not only we research on some state-of-art data science methods, we also focus on finding the most appropriate algorithm to solve the geospatial issues. We solve the problems like the optimization problem, prediction problem, and inference problem, and so on. So here I wanted to walk you through some of the methods we used in our previous project. So one example, one of the methods we used, we commonly use is geographically weighted regressions. So assume that, for example, the sales revenue for the merchants are affected by the local characteristics and behaviors. Then the GWR allows us to make predictions based on the data from the surrounding neighborhood. Another method we use to solve the spatial clustering problem is this HDTV Sky, hierarchical DB Sky. As we know, the regular DB Sky doesn't account for the variation in density. So the HDTV Sky, which is a hierarchical clustering method, can tackle this problem. It did a great job when my teammate Wenfei did her a million works in the park project. So she wanted to do a spatial clustering for human mobility data across the whole Central Park. But the problem is, as we know, there are different subregions in the park, and for each region, they have a different density of the data. So the regular DB Sky cannot do the clustering because it doesn't work. So HDTV Sky happened to be the method she used and to do this analysis, and it turns out that it was the most appropriate one, maybe one of the most appropriate solutions. And so another one, I think most of you are quite well known, is like the spatial autocorrelations. We can find out, for example, here we can find out where the hotspots of the car station in New York City. And actually there's more algorithm, more methods that we commonly use in our projects. For example, we use like the gradient boosting models to do the prediction, to use like the bandwidth spanning tree cutting methods to do the gray zoning problem, and like simulated annealing to do traveling salesman problem, like the PCA or the UMAP to do the dimension reductions, and then to speed up the following process, like compare the similarity or something. So yeah, that's about the algorithm, the methods we normally use. Okay, so we have the ingredients. We also know how to cook. So it's time for brunch, I think. Yeah. In CARTO right now, we focus on 5 core use cases: site planning, territory management, logistic optimization, geomarketing, and mobility planning. So I want to walk you through some of the examples we did, some of the use cases we did. The first one is a site planning case we did for food truck companies in New York. These companies wanted to know where they should relocate their food trucks, or if they wanted to add more new food trucks in the cities, where the new ones should go. So in general, for this case, we created predictive models using different data streams, including the census data, the point of interest data, the food traffic data, as I mentioned before, also the MRI data, the MasterCard data. Then we built the gradient boosting regression models. We start build the models only use like the census data or the normal data we can think about, and then we keep adding the new data streams to our models. And at the same time, we keep tuning the hyperparameters of the models and to keep to improving the performance of the models. And you could see here that one of the indicators of the performance, the R squares, become better and better, which means the model performance is improving. And we also list the feature importance here. So you could say, you can say the features from the new data streams play very important roles in these models. And after the model buildings, we predict the revenues for each grid cells across the whole cities, and this map shows the predicted values. But in this case, we thought the best plan is not to just say which single grid cell has the largest predicted values. Actually, we wanted to tell our clients which areas have a relatively higher predicted values, and they can make decisions by this. So we did a spatial autocorrelation analysis and do the spatial clustering for all of the hotspots. And finally, we picked the top cells in each areas, each clusters, and also recommend the places. Another case I'd like to show is a sales territory management case. So in these problems, there's a medical device company. It has 40 sales reps. In this map, the purple points, and across the whole Illinois state. And they have more than 900 medical centers, which are the yellow points here. The size shows its sales values. So they wanted to create a more optimized sales territories for their businesses. And we have to meet two requirements. The first one is each sales rep doesn't travel too much. And the second one, at the same time, each sales rep owns more evenly valued account, which means the sum of the sales values for each rep should be even or as even as possible. If we only take account of the travel distance here, the plan is quite easy because we just need to do the nearest neighbor search. So each medical center is assigned to its nearest sales reps. As you can see in this result, the territories do not intersect with each other. They are more independent because this is like the most spatially efficient solution. But the problem is the accounts are not fairly balanced. So we applied optimization methods called minimum cost flows. So not only the travel distance, we also consider the standard deviations of the sales values for each rep's territory. So in this map, the darker boundaries are the new results compared with the light boundaries. So I think it's not kind of obvious here, but never mind. So you can see the changes. Some medical center assigned to the reps that maybe is not the closest one. And also we tried different optimization methods. In this time, we used a genetic algorithm, and you can see in this map, a lot of the reps have to go to Chicago, because we know Chicago has a higher density of the medical centers and higher sales values there. So those reps have to travel further away to get enough sales. Well, this table shows the comparison in different solutions here. So for the baseline models, it definitely is the most spatially efficient one with the lowest total travel distance. But for the solution 2, as you can see, it has the lowest standard deviation of the sales, which means it's the most balanced one. But the problem is the runtime is much higher than the other two. So it's kind of a trade-off problems. And the solution for our clients can to decide which one they wanted to use based on their needs. Well, the third example here is the logistic optimization case. Well, a company wants to do a network optimizations to reduce the delivery cost. And the problem here is they have 6,000 parcels need to be shipped, and they have 5 warehouses and 13 fulfillment centers. So for each parcels, it will be delivered from the warehouse centers to the fulfillment centers and then to one specific delivery address. And in this case, we need to take 3 factors into our considerations. the travel distance, the shipping cost, and the processing cost. And we know the average cost from the warehouse to the fulfillment centers for kilometers per package. And also we know the cost from the fulfillment centers to delivery address. Then we know the processing cost per package in both the warehouse and the fulfillment centers. So our solution is the first step to generate these OD matrices to find out all of the combinations of the possible routes, such as the fulfillment centers do not exceed capacity limits, and all packages should be delivered to one delivery address. Then we got the objective functions here, and we run some operational research tools to minimize these objective functions, and here we got the results. So in this map, the warehouse, the red circle, and the fulfillment centers, the blue circle, are rendered in proportion to its capacity, and the black lines represents the number of parcels shipped from the warehouse to the fulfillment centers. And the colored regions here represents the coverage areas for each fulfillment centers. And that's our plan we deliver to our clients. And we also can see the cost, and the cost for the fulfillment center to delivery, and also the cost from the warehouse to the fulfillment center. Well, so those three use cases are just the use cases, but we wanted to deliver the solutions to our customers. I think from my understanding in CARTO, a solution doesn't mean just purely the data plus the algorithm and then show the results in the application or UI or something. So every solution is either for a specific type of problem or customized based on the client's needs, is supported by all of the techniques and products in CARTO. So from engineering perspective, Carlo Solutions covers from the data import API, from the data import API to the SQL query API, from the styling language to the map rendering engine, to all kinds of the techniques in CARTO will support the solutions. And there are actually some of the solutions we are working on. For example, this one's review, which aims to solve the set planning and set selection problems. And also this waterfall analytic, which shows the mobility and do some analysis on the human mobility data. Yeah, I think, yeah, that's all about my presentation today. Thank you.